Hello, everybody. Welcome to SRA 365. I'm, of course, Professor S. This is this week's lecture. Let's get into it. So, what we're talking about today or this week is simple regression. Let me kind of give you the scenario. So, say we have data that we have like an x-axis, which is like the predictors, the y-axis, which is the outcomes, and we're trying to determine the relationship between the two. And we want to kind of represent that with a line. So how do we do that? Like I said, with a line. And so it's very similar to lines that you have seen before, where we have y equals mx plus b, right? So where the slope is here and the intercept is here. The only difference is in stats, we don't really represent it in exactly the same way, but it's very close. Let me show you. What we do is we actually switch the values around. So we have the slope or the intercept first and then the slope. So this is the slope and this is the intercept. Okay. And so actually we kind of like don't use the b and the m. What we use is b sub 0 and b sub 1. Okay. And so this is like basically how the y values that we observe can be seen. So we have this is here it is color coded, but this is the model and this is what is error. So the y is the outcome that we want to try to predict. B1 is the B0, excuse me, is the slope, is the intercept. B1 is the slope. X I or is the x value at that value or at that index value. It's that specific x that we're talking about. The idea is it's kind of acknowledging that there's multiple x's. But x is overall the predictors, but speaking about that specific predictor at I with that outcome at I for y. That's what the i's are. And then the error is that things don't always line up on the model. And that's actually to be expected. It's not something that's wrong. It's just a feature. Let me kind of show you about like how this kind of looks. So if we have a dot that is outside of our line, which it was before in our last, in the when I showed you the graph before, notice that we have the specific x and the specific y that we have, and notice that that point's not on the line. That difference there, that height, is the error. In this case, the error is positive. If it was below it, it'd be negative. It's just part of it. We don't like actually, we'll get into like how close things are to our data, but it's like I said, error is like kind of good. We want to try to minimize the error. Yes, but we don't want zero error because that means it's the model is too close to the sample, and so it looks like it might not help us predict that well. Anyways, so we're also going to talk about prediction and confidence intervals. The idea is like the equation that we have helps to do two things. One, it can help us estimate a value, and two, it can estimate what we think the value could be. Sounds kind of the same, but it is kind of different. Like, so for instance, if you look at this data right here, notice that line fits that data, the scatter plot, very, very well. The issue is that not many of those points are on that line, right? So we wouldn't really expect many of the predictions to actually be that value. It'd be more of like what it centrally tends to be, right? So central tendency, mean. We think the mean's probably about that thing. And so with that kind of calculation, we have what's the confidence interval. Now, the way the confidence interval will work is that confidence interval like is a percentage, and we're not saying that we're that percent confident. We're saying that if we do the test infinitely many times, 95% of the times that calculation will have the correct value in it, the correct mean or the correct model or the correct line for the population going through it. Now, we wouldn't expect the population model to go through every single point exactly because our sample doesn't have it going through every single point exactly. And that's okay. That's just there's like other features in it. That's usually okay. But anyways, when we're thinking about it, here, let me put these values. So like when we're thinking about 95% confidence interval of these points, what we're thinking of is like that it's not necessarily coming up with an equation of lines. It's coming up with 2 points, a lower bound and an upper bound. And notice that at this this highlighted spot, this is a x value that has 3 different possible values. Now, of course, or 3 different outcomes observed at that one x value. Sometimes with whatever we're measuring, that's okay. That happens. So like if we're thinking about, let's say like if we're thinking about like age and height. So if we're trying to predict how tall somebody is based upon their height, and we look at a few different people, there's going to be people that are the same age at different heights. That's okay. But that doesn't mean we still can't use it to help predict heights. Maybe, I don't know. I'm just saying that that's an example, and that seems to be the case for this thing where we have multiple y values, because that's sometimes how scatter plots work. And so also furthermore with our model, it's giving us a central tendency for what we think those values are, right? And so the confidence interval gives us once again if we do this test, if we do this calculations, or if we do infinitely many samples of this size and do it at this calculation, 95% of the time it will be in that range. If we do a different percent confidence interval, it will be a different percent of the time. So if it's like 80% confidence interval, then 80% of the time the range would be in that value. So it's going to be a little tighter because not as many times is that value in it. So the idea is like the confidence interval helps get an idea for how accurate your model is. It's a data point, or in this case 2 data points, right? Or actually, as we'll see in a second, 3 data points. But you'll see what we're talking about in a second. The other calculation that we're going to be doing is the prediction interval. So the prediction interval is giving us an idea for what the values could be, the lower bound and the upper bound, meaning that once again, if we do this, the sample, an infinite amount of times, like if this is prediction interval 95%, 95% of those calculations would be in that correct, would be the correct range. So anyways, this is visually how it is. Don't worry about like how do you get those dotted lines. That's just to kind of show how it fits on the data. Notice that towards the middle, they're a little closer, and then as we get away from the middle, they get further apart. It kind of fans out. So it's not necessarily a straight line. It's kind of both the prediction interval and the confidence interval. Anyways, let's go through the code, and we'll come back here and we'll take a look at what the data has. Now, before we go into RStudio to see this in action, let's kind of review the data that we're using to know what we're using before we start using it, right? Anyways, so this is the reading that you are given. And you have access to this R script right here, but we will be using this data file in this video. So if you want to do it from home, in the video here, you see the video here that you've clicked on, maybe, or maybe you have you subscribed or whatever. But this is essentially the script that we're going to be using. I modified it a little bit where I have some blanks where I fill it in, but other than that, it's the same script. Likewise, this is or I don't know about likewise. Anyways, as I mentioned before, the data, file, this is exactly the same file. It's just linked to here as well. So it's in the same location. So these are the 2 things that we will be using for this thing. So let's go into R. Here we go, and notice that I already have the folder. I can't talk. I'm sorry, that we're trying to get into. And like I said, this is the one that you have in the reading, but this is the one. Well, this is the one that you are given, and it's very similar to this one, the one that we're using. I'm going to close out these real quick. All right. So I'm going to walk through, in order to kind of understand that walkthrough that we had, I'm going to go through the things in here to kind of illustrate what is in that walkthrough. Fill in the blanks, that sort of thing. So first of all, we got to get our data in. Wonderful. And let's take a look at what this looks like. So I'm going to plot that data. It's thinking about it. And here it is. Okay. Wonderful. Not something new. This is like old stuff that we've talked about, that we've done before. What we're trying to do is we're going to try to see if we can come up with a line to fit this. Next week, what we're going to be doing is kind of wondering if we should be fitting lines to things like this. Anyways, let's get into how do we actually make those models. So the way that we make these models is that we're going to, you create the models and then you can do stuff with them. In order to create the models, you need to have a name for it. I'm going to call it cyber attack here. And then once you create these models, you could do summary. And there's two different ways that you could do it. I'm going to focus on, I'm going to do both of them, and I'll show you which one I like better. So I'm going to use this name. This is the name that I want to use for each one of these models. The data frame that we are using is called cyber data. That's the one I put in here, this one right here. And that's what should be for each one of these data frames. The y-var and the x-var, we're doing response time is our x variable right here, and our y variable is the num attack. So we're trying to predict the number of attacks based upon the response time. So if we go into here, let's see. So our y variable, and maybe it's easier if I just start with the $sign here. Now I can do the number of attacks, and then our x variable here is response time. I didn't like that. Response time. Okay, so now it works. So then when we run it, here's what it looks like. Summary. The big thing is like, remember what the x variable is? It's cyber data $sign response time, right? So it's saying that it's the variable from this data frame. And that works, except this is kind of a lot. Wouldn't it kind of be better if it was just response time? That's what I'm here for. So what we can do is this format right here. And this is the one that I'm going to encourage you to use. So we're going to, first we put in the y variable, which in this case, this is num attack. And similar to the last one, we're using this thing to say that we're predicting this value by this value here. And then the next thing is the response time. I'm going to actually, just so I don't make a mistake typing it, I'm going to copy it and paste it here. Notice that I don't have to put the $sign because I put the data equals and then whatever data frame I'm using. So in this case, this is cyber data. Boom. And so that when I run these two lines, it doesn't like that I have this extra R here. Makes sense because that's not a value in our data frame. So I don't need both lines. I want just this line. It doesn't matter if I do both lines. It's still going to give me the same answer because it's going to run this, and then it's going to overwrite this variable with this line right here. So anyways, let's go back into the slides, and we'll take a look at what this data is, and then we'll come back and we'll talk more about it. All right, so here's the data that we had from that outputted from R, right? And so I'm gonna talk about like how this fits in with the data, or with our model. right? So these are the coefficients that we talked about, the intercept and the slope. You can tell the intercept because it's labeled as intercept. The slope is like it's the response time. So it's talking about what's the coefficient, that's the slope for that x value, which is response time. Okay, so that's what we're using. The next thing, the next two columns next to it, we're not actually, all the other columns we're not really going to use too much, not directly at least. Those are what we're going to need. So like if we're trying to create our model for predicting the number of attack, we can use those two coefficients and it would fit in like this. So we could predict what the number attack would be or tend to be, given that the response time is whatever amount of days. So if we plug in the number and multiply it to 0.09613 and then add that product to 134.1, that would be our our closest estimate for num attack, right? And then also, if you remember from the graph from before, we wouldn't expect it to actually be that exactly. We would expect some wiggle room, and we'll talk about how much wiggle room we would kind of expect. Before we do, let's talk about the R squared. The R squared helps us determine how good the fit is. In this case, it's 0.3347. The multiple R squared is saying that 33.47% of the number of attacks can be predicted by the response time, or 33.47% of the Y values can be predicted from whatever X variable is. Okay. Notice that there is another R squared here, the adjusted R squared. That's what we use for the multiple variables. We only have one variable, so we're going to, for the time, use the multiple R squared. It's a little confusing, but just go with it. So anyways, this R squared, since, like I said before, since we're using only one model or one variable in our model, we're using the multiple R squared. Okay. And as I said before, it's the percent of variability of the outcome that could be explained by the predictor. It also goes by so many different names, like the coefficient of determination, the squared multiple correlation coefficient, the degree of overlap, the shared variability between X and Y, yada, yada, yada. Yeah, depending upon whatever X and Y is. Now we can use our we're given R squared, and we can kind of figure out what R is based upon the data, and that helps us with determining what's known as the effect size. We'll talk about effect size for other things later on. But anyways, we evaluate the effect size using Cohen's cutoffs, and this is in the reading as well. So we say that less than 0.1, or a absolute value of less than 0.1, is very small effective size, very weak. In between 0.1 and 0.2, and these, once again, all of these are absolute values. I'll just say that once, because the idea is like R is either positive or negative. It depends upon if the if you look at the slope, that's really going to be tied to it. So like, for instance, the slope here is positive, right? It's 9.613, or as I put times 10 to the negative 2, or as I put it before, 0.09613. Notice that it's positive, right? And then also when we graphed it, like as X increases, Y increases. So that means R is also going to be positive. If it was the other direction, it'd be negative. And we'll kind of, I'll show you how to calculate R when we get into the data again. But anyway, so these are absolute values of R. So when we have less than 0.1, it's very small. Effect size, very weak. If it's between 0.1 and 0.29, it's a small effect size. And then we get into medium, into moderate. You guys can read, right? So anyways, that's what those are. The one other thing that I want to talk about from this data is the F statistic. So the F statistic on this whole line, we have, like, all these values are important, but really the the two things that we're going to focus on is the F statistic, which is part of the F distribution. We'll talk a little bit more about that in a second. And then the associated p-value is the less than 2.2 times 10 to the negative 16. So the idea is that R has an acceptable range. And so once it gets to a really, really small number, it says it's just less than that. So think about it, 2.2 times 10 to the negative 16. That means that there is, it's some value less than 0 point and then 15 zeros to 2. Let me show you what it looks like. It's some value less than this. This is super, super, super small, okay? Usually when we're talking about significance, that we're using the p-value. So and we want this to be, there's an arbitrary accepted value of 0.05, right? Because we really like 95%. And the way that we get the 0.05 is 1 minus 0.95. And so the idea is like the p-value is we want that to be, oftentimes we're looking for that to be really small. The idea is that the p-value is the probability of our observation occurring due to chance, that it just randomly occurs. It's essentially saying that there's no relationship between this. So the probability that there's zero relationship is very low, meaning that if we're doing a hypothesis test, the null hypothesis is that there's no relationship. The alternative is that there is a relationship. And so since it seems that it's very unlikely that there's no relationship, we would conclude it looks like there's a relationship based upon the evidence we've been given, right? That's what the p-values get. So since this value is less than 0.05, it looks like this is statistically significant. So anyways, as promised, the F distribution. So F value, there's a few different ways to calculate it. This is one of the ways. This is part of the F distribution. It is a ratio for how much the model is improved from the prediction of our outcome compared to the level of inaccuracy of the model. And it helps us determine the like I said, the statistical significance of R squared, right? So remember that was the multiple R squared. This helps us determine the associated p-value. And as it says here, the lower the p-value, the better it is. And usually we want, like, if consider default is 0.05 or 5%. So if it's less than 5%, then it's considered statistically significant. Okay, let's go see how to find some of these calculations in R now. All right, so now what we're going to do is we're going to go through the these different things along the way and fill in the blanks, right? Like I said, the blanks are already full in the thing that I gave you. This is to help kind of explain what blanks we need to think about filling in. So first of all, finding R. So we're given R squared here, which we talked about. It's right there. And so when we plug this in, so we're trying to find R and we have R squared, right? How do we do that? We find the square root of R squared, and that tells us what R is. Boom. So it's 0.5785326. Now, the only problem with this is that it's going to only return a positive value. So to kind of understand if R is positive or negative, we have to kind of look at the slope of our thing. And so here, notice that it's positive, so R is going to be positive. And if you need further evidence, I mean, look, the best fit line is going to go up this way. If it was negative, it'd look down like this, and that doesn't make any sense. So we know R is positive. R squared will always be positive. All right, anyways, so now the thing is like we want to do some predictions. So we have our model here, and so I'm just going to copy these values in. So first of all, we have our intercept, and we can just copy this in even though it's in this scientific notation. And I can put these values in. So then notice that this like of that form. There we go. And so notice, oh, the days. We want to predict it at 1,250 days. So 1,250 days. And so we run it. And so here we have 254.2625. So at 1,000, so it should be about here. We're thinking that it is 250, which is probably around here. So it's thinking that the value according to the model would be about here. Now, let's kind of reflect on a couple of things. So first of all, with the best fit line that's going through this data, remember that it's not necessarily it's to help us predict. Like this is quite the spread, so we're going to probably expect that there's going to be some variance that's acceptable, but that's where, or we think that typically that's where that value should be when at the 1,250 days, which should be at this white line right here. So right at about here, this is probably where the line's going to go. Let's kind of get that line to kind of see that IRL. So here I'm going to do a plot, and I'm going to plot that model into this graph right here. So we're going to do another plot here. So we're doing the plot itself, and we want to do the model, which is in this case actually, you know what? Not going to chance it by typing. I'm going to copy and paste the model here. And this is also the model that we're referring to. So this line is going to be based upon our model. So we want to make sure that that's what we put in there. The next thing is we need to put the xvar. Remember our x variable right here, the thing that we're using to predict is the response time. So we need to put that in for our value right here, which is not, I did not copy. So y or xvar, and then this other x variable here. And then since we're trying to, the y variables right here is from the number of attack, that's what we want to put on that section right here. Here, I'll do this more accurately. Where is it? Y variable. Boom. So now we've put in the location for each one of these. Let's see how this graphs. There we go. And so notice that we have a line through our data right here. And remember, our prediction before was about right here, right? And it just calculated where that location is on that line, or estimated that location on the line. And notice that we would probably expect like some healthy range just depending upon this sort of thing. And that's where like the next things, the next values pop in, where we have the prediction things to predict the confidence in the prediction intervals. So in order to do that, first we put in the model. In this case, it is cyber attack is the model that we're doing. And really, this is the same for both the prediction and the confidence interval. I'll do both of these at the same time. And then the next thing is we put in what the x variable is for that thing. In this case, we're talking about response time, and we want it to be in 1,250 days, excuse me. So we put in the variable name, and then we have to put in the value. In this case, 1250 and 1250, right? And so then the next, for the confidence interval, we want to make sure that this is confidence. And then the prediction interval, put prediction, and then the level, this is the percent that we're looking for. So the 95% confidence interval, that's what this is going to find. If we want to change this to the 80% confidence interval, it's 0.8, right? So anyways, I'm going to keep it at 0.95 because that's the arbitrary value where we like to do these things. And let's just run and see what we get. Notice that we get three values here. We get the fit, the lower and upper. So do you remember from the slides from before we had the lower, that's where that line that goes kind of like this underneath for the confidence interval. Remember, the confidence interval was really close to the line. That's going to be, again, like about where we're thinking that the line is. We're not thinking those are the possible values. We're thinking that that's where the model should be for the population. We're trying to, like the whole thing is we're trying to guess what the model is for the population based upon our sample. And the 95% confidence interval is saying that if we do this infinitely many times, 95% of the times, the actual model will be in that range, right? So in this case, for this calculation, it would be, the lower would be 239.1171, and the upper would be this amount right here. I'm not going to say it because I can't talk right now. But anyways, notice that we can find out the difference between those two, and notice that it's 30.3583. So that's how far apart those two values are. If you divide that in half, you get the margin of error, by the way, for that specific value. The last one that we run here is the prediction interval. And so remember, this is like the range of where we think the prediction would be at that value. Like, what is a possible value at that? Not like where we think the model is, but where we think a value could be. And that's what the prediction interval tells us. So then when we run it, notice that it gives us a fit, which is the same as the other one, gives us a lower limit, and it gives an upper limit. So this is the upper limit here. The upper limit is going to be up here where it thinks about the possible values that the thing could be, and the lower limit is going to be down here where it thinks that the values would be. And so that range, notice, is going to be much bigger than the confidence interval because it's a bigger range, right? So the prediction interval is thinking about where the predictions, where values could be at that location. And the confidence is essentially the mean of the predicted mean at that location. So what we think typically would happen. The one other thing that I want to point out before I finish is that notice that when we're doing these prediction values, that we're not doing we're not going beyond our data. The idea is like, in order for these predictions to work, it has to be in the realm of our data. So like the reason why we're looking at 1,250 days is we have all this data. And so then we're thinking like, all right, so our range is between 0 and something bigger than 2,000, maybe 2,050. 2000, not 2015, 2025, 2,250. There we go. Sorry, I'm talking. But anyways, the idea is like it's in that range. That's as far as we can predict, because that's as far as we know. When if you're thinking about predicting beyond those values, that's when we get into forecasting, and that requires a lot more consideration. It's much more difficult than to predict the future or predict beyond our values than it is to predict within our values. And so that's why we're going to start within our values here. So the idea is like we have all these values here, and so we'd consider like, well, about what we think we should expect. And that's where we use this model for finding about what it should be within the range that we have already picked. Right. Anyways, I think that's good for this week. I'll see you all later. Bye. Hey everyone, hope you enjoyed that video. If you did, please press the like button below. It lets me know I'm doing something right. If you have any questions about any of the content, please send a message to both me and the rest of the teaching team in Canvas, and we will get back to you as soon as possible. Don't send it through normal email. You will not get as fast response. If you have any suggestions for how I can make these videos better, please leave in the comments below. Don't forget to roundhouse kick the subscribe button and ring the bell to get notified for the next video. Anyways, I think that's good for now. See y'all later. Bye.